Good morning. This is Adam Wise, Andor Technology at Oxford Instruments Company. And in this short video, I want to show you some features that will help you synchronize your camera with your other equipment in your lab, help with troubleshooting experiments, and maybe clarify a little bit the way that the camera actually works. Specifically, this is a Newton 920, a high-speed scientific full-frame CCD often used in spectroscopy experiments. I'm going to show you a little bit about triggering and how to monitor the exposure of the camera over its fire output port. So first I'm going to show you what this camera actually is in Solis. So Solis is our control software for all of our cameras, although we can work in a number of other venues as well. I'm going to take one image with this take signal button. I've got my cooling totally off, so this is just junk right here. But I just wanted to show you the metadata of the file that will show you the camera type. So I'm going to access that metadata, which is all of the associated information about the measurement that kind of will help you after the fact keep track of what your measurements actually are. With the I button here in Solis, this little information button. So this will show me everything about the measurement that is relevant, that you can set in this program. So specifically, this is a DU920-BEX2DD. It is a full-frame scientific CCD. I have the spec sheet right here I can show you. So this is the quantum efficiency curve here in solid red that goes all the way from 1100 nanometers in the near infrared to 300-ish nanometers in the UV. So it's a really broadband anti-reflection coating sensor that's useful for a kind of a wide range of spectroscopy and imaging experiments. So what I'm going to show you primarily is about triggering and about monitoring the exposure. So on the back of the camera, and here's the manual for the Newton, we have our TTL logic inputs and outputs here. TTL is just a way of specifying the voltage levels that signify off and on. We have an I2C port for communication. That's a low bandwidth microprocessor to microprocessor bus just for communicating serial information. We have a USB 2 port for data and control, and a power input. So that's going to come from the power brick. So this is the rear panel. So what I'm going to do is I'm going to bring a trigger in from actually from an Arduino that will be my function generator, and I'm going to monitor the exposure of the CCD on the fire line. So when I send a pulse into the external trigger, the exposure will begin, and during the entire exposure, the fire line will be TTL high. So that will help me synchronize with other experiments, synchronize with other equipment, show when the camera is actually exposing, and show when the camera is finished exposing. So let me go back to Solis here. I'm going to close this metadata window, and I'm going to open up. I have a small desktop oscilloscope called a picoscope that I highly recommend that will kind of monitor the situation for me. So I'm going to split the window here and have a little view. So right now I'm going to go to about, let's see, start this. And here's my trigger pulse. That's coming from the Arduino, and that's got a 1 millisecond on, 500 millisecond off time. I'm going to go to my acquisition, and I'm going to start by using the internal triggering. So internal triggering means the camera runs when it wants to run. So when it finishes a frame, it starts the next frame. If I'm doing a single acquisition, it's going to take one image and it'll be done. But if I run a kinetic series, which is to say a movie, and I capture multiple frames one after the other, in internal triggering mode, it will do a, whoops, wrong one. In internal triggering mode, it will record a frame, and then as soon as it's ready, it will go right on to the next frame, regardless of what else is going on. So it's running on its own clock, internally triggered. I'm going to set a 1/10 of a second for the exposure time, and this will show me the actual frame rate in hertz, or the number of frames per second I'm getting, or the interframe timing. So I'm getting just about 5 hertz. A little bit of overhead. You'd expect 1 over the exposure time for it to be the frame rate, but we have a little bit of overhead happening for readout, so that's why it's just below the 5 hertz that you'd expect. So I'm going to hit OK here. Actually, I'm going to go back and set a high number of frames just so I don't run out while I'm talking. So I just want to show you what happens when it's internally triggering. So right now, the fire is happening whenever it's happening. This is showing the actual exposure. It's not synced to the external trigger, so this is just happening perfectly fine, but this is just running on its own clock. It's exposing when it exposes, then we have a readout, and then the next exposure. So I'm going to stop that for now. When I switch to external triggering, keep everything the same. I'm going to make sure keep clean's enabled. I'll talk about what that means in a second. And if I run this measurement now I'm getting an exposure with every trigger pulse. So as long as my trigger pulses are coming in a little bit longer or equal to the interframe spacing or the cycle time that I had in that previous measurement, previous window. Go here. So minimum trigger period, 0.2 seconds or 4.8778 hertz. As long as my triggers are coming in more slowly than that, I will get one exposure per trigger. And again, it's not a big deal if triggers come in faster than that, but I'm not going to get an exposure for a trigger that comes in before the next one is ready. So here you can see the blue trace, again, is my fire, and the red trace is the trigger. So we have trigger, exposure, and then this fire signal actually shows me when the CCD is live recording data or capturing information. So if I change the exposure time, it will actually give me a different value here. So I'm going to drop that exposure time to say 75 milliseconds. Do this again, and I got 20 milliseconds per division, 1, 2, 3, and change. So I have 75 milliseconds here. My trigger is the same. So to go back to what I said about keep cleans, if I zoom way in time, now I'm at, where are we here? 50 microseconds per division. We can see the leading edge of our exposure is actually lagging the trigger by about 50 microseconds with some jitter, although it's not real jitter, it's due to the keep clean cycle. So my question is, say you're doing an experiment where you really need that exposure to happen as quickly as possible relative to the trigger. And this is the case for all of our CCDs. Normally they'll have a keep clean cycle. What is that keep clean cycle? Well, we want to make sure that the counts that we're getting, the photons that we're collecting, are only due to signal that's captured within the exposure time. So what happens outside of the exposure is that we're constantly running sweeps of the sensor that dump the charge that's building up, both through out of window light and also any thermal counts that happen. We want to dump those before we actually take our measurement. So what we're doing is constantly sweeping that charge out. Then when we run the actual measurement, which is to say the exposure, then we stop keeping clean and we say, okay, let's collect some real charge now. So the exposure time will always be the same, but the question is, can we get rid of that little period? Sure, we need the lowest latency possible on our exposure. Say you have some pulse laser that's doing something, causing some phenomenon to happen, and you want to catch it as quickly as possible. How do we get that sync up? This becomes a real issue with our time-gated cameras, so I just want you to understand kind of what that does. So now if I go back and I turn off the keep clean cycle with this, and you can see it's recalculating the minimum trigger period a little bit as well. We rerun. Now we're much closer to the actual trigger. So if I zoom in even more, you can see we're closer to 1 or 2 microseconds to the beginning of that. And again, that might be due to the exact value that might be distorted a little bit due to the oscilloscope that I have, which is a really wonderful desktop Picoscope 2000, but it cost about $100. So I wouldn't trust its super fast timings. Although it's a fantastic desktop oscilloscope. And then my cabling is kind of all over the place as well. So I would probably get a nicer oscilloscope to actually quantify that value there. Finally, I want to show you one more triggering mode here. So this is another option that we have, which is not external, but external start. So external start is like external, but rather than one exposure being triggered by one trigger pulse will start the entire measurement sequence here. So say I'm measuring 10 frames at some short exposure time, so say 10 milliseconds or something like that. External start, I get one trigger pulse, and all 10 measurements will go as quickly as possible. So there are situations where you want to measure multiple frames set off by one trigger, by one event, but you don't want to have to individually trigger them. You want them to happen as quickly as possible. So I might need to zoom out to actually see this. Oops. Change my time per divisions. So now you can see the individual triggers coming. And if I run my measurement, so you'll see all the frames will pop off after one trigger pulse. Do this again. So the next available trigger pulse will pop off all the frames. So again, that's another option that you have. All right, well, I hope that made things a little clearer. And if you have any questions, feel free to email me, a.wise@andor.com, or visit the Andor website. And have a good rest of your day.